And I would like to emphasize on rotation operators. And I would like to exemplify at the end certain quantum logic gates. Yeah, they use in quantum computing. So we've already explored the idea of the block sphere. So the block sphere gives a nice visual juicy representation of a spin half two-level quantum system. And the block sphere goes as follows. We draw a sphere of unit radius. On the north pole lives the plus z quantum state. On the south pole lives the minus z quantum state. And these states are eigenstates of the sz operator. So if we have the sz operator acting on plus z, we would get h bar over 2 and the state will be recovered. If sz acts on minus z, we will get minus z and the eigenvalue would be minus h bar over 2. So plus z and minus z are the eigenstates of the sz operator and they are orthogonal. So the inner product between the plus z state and the minus z state is 0. So on this block sphere, these points are on diametrically opposite sides of the circle. So from a geometric perspective, in 3D space, these points do not look orthogonal. Okay? But the emphasis I would like to make is that we're not talking about the 3D Euclidean space. We're talking about the two-dimensional quantum system, which lives in a special kind of space called the Hilbert space. So orthogonality does not necessarily mean that a point here and a point here would be orthogonal. Here, orthogonal quantum states live on diametrically opposite sides of the sphere. So if I have a point here, a quantum state that is pinpointed by this point on the sphere, its orthogonal state would lie at the far end. So if this is the state x, this would be its orthogonal state at the diametrically opposite point. Okay. And this get x is defined as an equal superposition of z and minus z states. Okay. And if I have a minus sign here, you get a minus sign here. Likewise, if I have a point here, which is actually a quantum state, because every point on the sphere is a quantum state. If I represent this state by y, then the diametrically opposite point would be here on the west cardinal point. This would be minus y. And these states would be orthogonal. And we've already defined these quantum states as the following. Z plus minus iota minus z. So this is just a recap of our previous lecture. Nothing new about it. Now what we would like to talk about, we've talked sufficiently about quantum states, and in a two-level system, two-level quantum system, these are actually points on the Hilbert's, on the block sphere. And you need not be on the equatorial plane. You need not be on this meridian. You could be at any arbitrary point. So if I take this point also represents a quantum state. So this point P would correspond to a state which has a general form cosine theta by 2 ket z plus sine theta by 2 e I phi ket minus z. Right? This is a general quantum state where theta and phi are real angles, which are the polar angles of this point. So this angle is theta, whereas this angle is phi. So any point on the sphere is represented by two real numbers, theta and phi. So you vary theta and phi, you get different quantum states. The coefficients of the eigenstates of Sz are given by cosine theta by 2 and sine theta by 2 into Ei phi. So this is something we explored earlier. Now, this two-level quantum system models a spin-half system, like the spin of an electron, the spin of a proton, the spin of a neutron, the spin of a photon. It could also model the polarization of a photon. Here, this becomes ket H, this becomes ket V. Alright. This becomes ket H plus ket V, which is the 45 degree polarized photon. This would become left circularly polarized light. This would become right circularly polarized light. And so on. And this is elliptically polarized light with an arbitrary angle of theta and phi. So the polarization of a photon and the spin half particle, from the quantum mechanical perspective, they behave identically. These are different physical systems, but they have a common quantum description. Yes. देखो एक फोटॉन है जिसकी पोलराइजेशन डिग्री ऑफ फ्रीडम की बात हम करें तो this could be ket H, this could be ket V. All you need to know is that there are two orthogonal states that form the basis for this two-dimensional system. So the polarization of a photon is a two-dimensional quantum system. So the polarization can also be modeled, the states can also be specified by points on the surface of this block sphere. So now the polarization of photon is something totally physically different from the spin of an electron. The path a photon takes in a beam splitter experiment, it has two possibilities. So all of these disparate, apparently dissimilar physical systems have a common quantum description. Okay? That's why sometimes you call the polarization of a photon as a fictitious spin. And in the language of quantum information processing or quantum computing, this two-dimensional system is also called a qubit. Okay? A quantum bit. A bit is generally just 0 or 1. But quantum mechanics tells you that you can have superpositions. You can have ket 0 plus ket 1. You can have ket 0 plus Ei phi ket 1. So quantum mechanics gives you a diverse array of possibilities of quantum states. So this is what a qubit is. It's just a two-level quantum system. Okay? Boolean logic is also two-level logic. You can have 0 and 1. But there's nothing quantum about it. You can't have a superposition of 0 and 1. But quantum mechanics admits or allows or enables these superpositions. And this is where the real power of quantum information processing lies.
So this on a purely on a discrete mathematical basis इसमें difference किस तरह पड़ेगा this superposition? मतलब आपके पास Boolean logic है तो दो states होंगे which would give you processing on the basis of 2.
So if you would like to have a NOT gate, 0 goes to 1 and 1 goes to 0. This is the truth table of a NOT gate in Boolean logic. In quantum logic, so in Boolean logic, if you would like to apply a NOT gate, you first initialize your bit as a 0 and then apply a gate, you get 1. Then you initialize your bit as 1, you apply a gate, you get 0. In quantum mechanics, if these were qubits, you could prepare this state in one go and apply a quantum NOT gate, okay, and you will get an output. The output in this case will be the state itself. So you can have multiple inputs at the same time and you can perform an operation on all of these quantum states at the same time in just one experiment.
So with quantum computing, it's more about reducing the number of steps.
Yeah, this is just one aspect. It's a huge field. Just one aspect. Quantum information, one aspect is that superpositions allow quantum parallelism. You can have parallel operations on multiple states in just one experiment, in one go. Alright, so let's look at this block sphere again. Now what I would like to do is, I initialize my state, it's in state Z. Now let's think about three axes. Let's call this axis the x-axis, the y-axis and the z-axis. Remember, these are just labels. They have nothing to do with the real Euclidean space. Okay. Now what I would like to do, my starting state psi in is z. Okay. Now I would like to rotate this state, which means I would like to apply a unitary operator on this state, such that my final state lands up here. So I want to apply an operation so that I start off from ket z and I land onto ket x. That is, I want my final state to be ket x, which is an equal superposition. In other words, if I make a block diagram, a logic diagram, I have some unitary operation. I input the state z and I would like to go, my output state should be x. Okay, so I need to apply a unitary operation. It's just a rotation is a unitary operation. So I label this operation by r. I would like to rotate by pi by 2. And what axis of rotation should I choose? The y-axis. So I label this operation as unitary operation, which is of course a matrix when represented in a particular basis, by r about the y-axis and pi by 2. Now, I would like to look at the form of this rotation operator. Where does this rotation operator come from? And what is its mathematical representation? This is what I would like to do. So this is my axis of rotation. This is my axis. Now suppose I apply Ry through an angle theta on the state, initial state z. Now, what is my final state? It should lie in which plane? In the xz plane. ठीक है? तो ये जो plane है ना, जिसको मैं बनाने की कोशिश करता हूँ यहाँ पे इस तरह, इस plane में lie करेगा, ठीक है? So this is my initial state. I end up on the x-axis, but this is the plane that I am traversing. So I apply a rotation operator through theta, I end up somewhere. My final state could be somewhere. So if I draw this circle, a meridian circle, is zero longitude की line है, so my final state would lie somewhere here. So if my rotation is through theta, right? This is the axis of rotation. So I start here and I end when this angle becomes theta. Okay. So my angle by which I am depressing my state is theta. So I end up here. यहाँ से मेरी बात नूर. तो ये जो स्टेट है, इस स्टेट की अगर मैं किसी बेसिस में लिखना चाहूँ, ket z minus z की बेसिस में लिखना चाहूँ, तो ये स्टेट क्या है?
Cos theta by 2.
शाबाश, it's cosine theta by 2 ket z plus sin theta by 2 माइनस जी, और फाई क्या है? जीरो, क्योंकि इस मेरिडियन सर्कल पे, जीरो लॉन्गिट्यूड के सर्कल पे फाई की वैल्यू जीरो. देयर इज नो azimuthal angle. So this is my final state here. So initial state, the operator acts on it, and this is what I should get. Now if I rotate through a small angle, d theta, right? If this angle is very small, then my final state, this will become d theta by 2, and d theta is very small. So it's approximately 1. I get z here up to the lowest order. This sin theta, theta is replaced by d theta. D theta is very small, and in small angle approximation this becomes d theta by 2 minus z, right? So if I rotate through a small angle. Okay. Now this is my initial state, and this is my initial state, and this is the approximate final state. Now what I would like to do, I would like to replace. I would like to define a new operator. G, which acts on the initial state Z and gives minus I okay, what I would like to do is minus I G I would like to call this is a cat, right? This is a quantum state on its own. Agree? It's just a cat multiplied with the number. I would like to call this new cat minus iota g z, right? This is what I propose. This is d theta by 2 minus z. This is what I propose. Okay? I propose an operator g, I call it g, which acts on the initial state. And this minus iota is just a number. So I adjust my g such that minus iota times the operator g acting on the initial state gives me this. Okay? I want to choose a g such that I can write d theta by 2 in this form. If I choose such a g, then this expression r by d theta z becomes approximately equal to cat z minus iota g acting on z. Alright? I can always choose such a g, an operator g which acts on the initial state in this fashion, that g acts on the initial state to give me this. Okay? Or I can also write this as g acts on the initial state to give me the orthogonal state with plus iota over 2 d theta. Oh, sorry. This d theta isn't here. Okay? This is 1 over 2. I'm sorry. This is 1 over 2. There's no d theta here. Okay? So there's d theta here. Okay. So I choose a g. I replace this factor by I call this minus iota d theta. This d theta is just is retained. So minus iota times d theta times g acting on z gives me half of minus z. Okay? Alright. So under this prescription, ry acting on z is approximately equal to this. Okay, I'll give you half a minute to just decipher if the algebra is making sense. It's just algebra.
Sir, ry theta by 2 to z, you cos theta by 2 z plus sin theta by 2 into negative z. Shouldn't it be a mixture of projections on the z and the x scales? Because you're rotating in that angle.
Right, so this, you can express it in whatever basis you like. You can express it in z minus z basis, or
I'm not understanding why negative z. How does the negative z make sense?
because this is the general state. Generally, if you are at this point, this is the most general state you can write. You don't want to mix bases. You either choose one basis. So the bases are two orthogonal states plus z and minus z. So there will be coefficients with these orthogonal states. That's it. Okay. ये बात समझ आई? ये अलजेब्रा से इस अलजेब्रा को सामने रखते हुए हमने ये लिखा है. Now this becomes identity minus iota d theta g acting on z. ठीक है? ये समझ आ गई बात? Now if I do ry, I rotate through theta and then I if I rotate through theta as well as d theta, so I rotate through theta plus d theta, and my initial state is still z. Now, if my axis of rotation is the y-axis, and I rotate through d theta, and then I rotate through theta, I can do this rotation in any order, because my axis of rotation is still y. Okay, and I can first do the rotation through d theta, and then do the rotation through theta. It doesn't matter, the order doesn't matter, because I am not changing the axis of rotation. Okay. Hence, I can break this rotation through theta plus d theta into two parts. I can do a rotation through d theta, and I can do a rotation through theta, right? Acting on z. ठीक बात है. So, but my r by d theta is given by this. My r by d theta is given by identity minus iota d theta g, and this is given by, likewise, what would this be given by? Identity minus iota theta g, acting on g. G is some operator, we have to decide what is this operator. But there has to be some operator g which acts on z to give you minus z. Okay, it's such an operator which acts on z to give you the orthogonal state. It's like a NOT gate. Okay? It's some operator, we have to decide what this operator is. For the time being, I'm just writing this operator as g. And why g, I'll let you know in a minute. So if I carry out this multiplication, right? Now looking at the left hand side and the right hand side, I get r by theta plus d theta equals. I don't need to expand this, in fact. I can still call it r by theta. Okay? So the left hand side is r by theta plus d theta. I forget about the quantum state because it's common to both sides. I get r by theta plus d theta must equal the identity operator minus I d theta g multiplied by r by theta. Okay, I'm not decomposing this. Okay. Now let's do the multiplication. Identity multiplied by this operator is just r by theta, and this factor becomes minus iota d theta g operator acting on r by theta. Okay. Now take this r by theta to the other side of the equation. I obtain r by theta plus d theta minus r by theta. This equals minus iota d theta g r by through. Now I take d theta to the right hand side. I bring d theta here. This d theta vanquishes from here. I take the limit that d theta is very small. This just becomes a derivative. Now when this becomes a derivative, I have d by d theta of the rotation operator through theta equals minus iota g times r by theta. Alright. Now at this point, at this juncture, I would like to propose what is g. G, I use the operator, the letter g, because I want this operator to generate rotations. It's an operator that generates rotations. It acts on ket z to give you the orthogonal state with some amplitude, right? So it generates rotations. That's why I use the letter G. If I generate a rotation about the y-axis, then I propose that this G must equal the spin angular momentum operator Sy divided by h bar. Okay? I propose, and we have to check this out. क्योंकि मैंने इस d थीटा एक नंबर है, मैंने डिफाइन किया है कि ये minus I times gz gives you half of minus z. This is how I have defined g. Right? So this is how I have defined the g. Right? So d theta just carries over. I have d theta here and I have d theta here. So I propose that if I am doing a rotation about the y-axis, then my generator for rotation is the spin angular momentum operator along the y-axis divided by h bar. Okay. Let's see if this makes slight sense. Look at this. Look at what I have here. Gz acting on z. This is my definition for z. ये definition थी ना? मैं एक ऐसा ऑपरेटर ढूंढना चाह रहा हूं जो get z पे एक्ट होकर ये दे रहा है. ठीक है? तो suppose my g is what I propose over there. Suppose my g for this particular rotation is what I propose sy over h bar. So if this operator Sy over h bar acts on ket z, let's see what I get. Now what is Sy? Sy is h bar over 2 into the poly operator by operator, right? This 1 over h bar is part of my definition. Now this is acting on ket z. This h bar cancels out. And I have 1/2 sigma y acting on z. Now what is my sigma y? My poly operator sigma y is simply 0 minus iota 0. If this operator acts on z, now what is sigma y? Sigma y is minus iota z minus z plus iota minus z bra z. If this operator acts on ket z, sigma y acts on ket z, what is my result? It's iota. देखो iota आ रहा है ना? आपका नाम क्या? आयनूर। आपकी ईमेल आईडी क्लास के बारे में देखो ये आयोटा आ रहा है कि नहीं, ये समझ नहीं पा रहा. ठीक है. Now this operator when it acts on ket z, the answer is iota ket z. नहीं ये वाला ये इनर प्रोडक्ट नॉन जीरो होगा. देखो यहाँ पे ket z पे एक्ट हो रहा है, this becomes 1, this becomes 0, this goes away, so my answer is iota into minus z. ठीक है. So my result is iota over 2 minus z, which exactly matches this. So my choice of putting this generator for a y rotation as Sy over h bar makes complete sense. Okay. The angular momentum operators generate rotations. Linear momentum operators we learn later generate translations. Okay. So if I have a rotation about the y-axis, my g must equal this. Okay. Now let's look at this differential equation. D by d theta of the rotation operator which is the rotation about the y-axis, must equal minus iota sy over h bar r by theta. Now this is a simple differential equation that I can solve. The solution is simply r by theta equals exponent minus iota theta, which is the variable, sy over h bar. ठीक है ना, यही solution है ना इस equation का. You can check this. You can take the derivative of both sides. You will get this result.
So to the power of sy
G. अब देखो, rotation about the y-axis through an angle theta is given by the exponent of minus iota times the angle through which the rotation is taking place and the operator. Which operator? If you're doing a rotation about the y-axis, choose the sy operator and divide it by h bar. If you're doing a rotation about the x-axis, your rotation operator is e raised to power minus iota theta, that is the angle through which the rotation is taking place, and the generator for the rotation, which is in this case sx over h bar. If you're doing a rotation about the z-axis, remember these are axes in the Hilbert space, then your rotation operator is e minus iota theta s z over h bar. Now probably this is the first time you are actually observing an operator in the exponent. Okay, so I'll elaborate on this in a minute. How do you calculate such exponents? You don't have the index or the exponent now doesn't have pure numbers. It's an operator that's popping up in the exponent. So how do you calculate such exponentiated operators? Right? But the general rule is that if I want to rotate about any axis, I take the exponent of minus iota times the angle through which I am making a rotation, and in order to specify the axis of rotation, choose the corresponding angular momentum spin operator and divide by h bar.
Sir, I'm not getting good differentiation, so doesn't become sense.
ये खुद करो यार, calculus 2 है, ये खुद करो. dy by dx है, ये माइनस आयोटा y है, ठीक है, सम फैक्टर है c. y को नीचे ले जाओ, दोनों साइड्स इंटीग्रल वही हो जाएगा. All right. So now first question, is the r that we found a unitary operator? Should it be a unitary operator? Yes, because it's a rotation. Now the exponent of any operator, e raised to power a some operator, is defined as identity plus a square over 2 factorial plus a cube over 3 factorial and so on. This is how we define the exponent of an operator. Now we have to prove that r is unitary. Okay? So if I take, say, ry through theta, this is e raised to power minus I theta sy over h bar. If I want to find the Hermitian adjoint of this operator. I want to find the adjoint of this operator, right? Now the adjoint of this operator means that I have to find the adjoint of every scalar and operator inside this expression. So the adjoint becomes, what's the adjoint of iota? Minus iota, but there's a minus sign already there. So I get plus iota. What's the adjoint of theta? Is a real number, it's theta itself. And what's the adjoint of sy? Sy dagger. What's sy dagger? It's sy itself. Because the poly spin operators, they are Hermitian. So I get sy, h bar, right? Now this is basically ry through an angle of minus theta, right? Now, is this operator the inverse of this operator? Just without the dagger, this operator is simply the inverse of this operator. Because if I multiply these two operators, I will get identity. Hence, R is indeed a unitary operator when it is given in this form. R is all, it has to be a unitary operator because it's just carrying out a rotation operation. Okay? So the general form of a rotation operator is what I have outlined over here. Now how do we calculate the exponents of rotation operators? This is something we would like to see now. For that purpose, I would like to prove a theorem. So basically, I am exponentiating spin operators. Suppose I have E raised to power iota some theta. I don't use a minus sign because I am going to prove a theorem. Theta is a real number, can be positive, negative, and I have some operator A. Okay. I want to find out how in the world can I calculate these exponents of operators. For that I am going to prove a theorem. Now this operator A is such that A squared is equal to A. It's equal to identity. Okay? A squared is equal to identity. Suppose A has this property. It's an idempotent operator. A is equal to A inverse. Oh, sorry. It's not idempotent. It's not idempotent. The square of A is just identity. Okay? The square of A is identity. It's not idempotent. Sorry. Alright. Now, if A is such a matrix and I have this form, now what is this equal to? According to the definition of the exponent of an operator, I must be able to write what I've written over there. So I get identity plus A. Now the whole operator is I theta A, right? Right? I'm just using this formula. So now I have some scalar here. So the operator is the scalar times the operator itself. So I theta A plus I theta A squared over 2 factorial plus I theta A cube over 3 factorial and so on. Okay? Okay? This means identity plus I theta A. Now let's look at this expression. I square is minus 1. Theta square is theta square. A square is identity. over 2, right? 2 factorial, okay? Now let's look at this. I cube is I times I square, which is minus iota. So I put minus iota here, theta cube. What is A cube? A cube is A over 3 factorial and so on. Let's put in another term. I get I4. I4 is I squared square, which is plus 1. Plus 1 theta 4. A raised to power 4 is identity. So I put identity matrix here over 4 factorial and so on. Now let's look at the terms that have just the identity with them. This term, and this term, and so on. So the 0th power, the 2nd power, the 4th power, the 6th power, and all of these terms are such that I can write 1 minus theta square by 2 factorial plus theta 4 by 4 factorial minus theta 6 by 6 factorial and so on. And this is a scalar number and it's being multiplied by the identity operator. Plus an iota. Okay. Then I have theta minus theta cube by 3 factorial. I will have a theta 5 plus 5 factorial and so on with an operator A. Now what is this? What I've written in green, what is this equal to? It's a cosine. Okay, cosine of theta identity plus, what is this? It's the sine. Sine theta A. This is E I theta A. So if this property is satisfied, then the exponent, this exponent equals cosine theta identity, something that is easy to calculate, plus I times sine theta into the operator itself. Everything is very easy to calculate. ठीक है? अब हम देखते हैं कि हमारे रोटेशन ऑपरेटर इस फॉर्म में है या नहीं है. ठीक है? अगर यहाँ माइनस होता तो यहाँ माइनस आ जाता. ठीक है, क्योंकि साइन थीटा नेगेटिव हो जाती है, पॉजिटिव भी रहता है, ये नेगेटिव बन जाता है. ये समझ आया? ये थ्योरम एक प्रूव किया हमने. Now let's use this proof and see if we can simplify the form of our rotation operators. Alright. Suppose I choose E based on minus iota theta Sx over h bar. Right? What's this? This is the rotation operator about the x-axis. This is simply R about the x-axis through an angle theta. Right? Now what we would like to see, if our exponent is such that if it's in this form or not. I would like to see if my operator, which is being exponentiated, has a square that equals the identity. Okay? Now one thing you would like to observe is that if I take sigma x, which is simply 0, 1, 1, 0, if I take the square of sigma x, its identity. Likewise, the square of sigma y is identity. The square of all the poly operators is identity. Okay. But our Sx, our S alpha, where alpha could be x, y or z, S alpha is really the poly operator divided by 2 multiplied by h bar. So if I multiply the spin operator by 2 and divide by h bar and then I square it, I will get the identity operator. ठीक है ना? अब ये h bar naturally मौजूद है, लेकिन ये 2 मौजूद नहीं है. ठीक है? So I artificially put a 2 here and I divide by 2. Right? Now this operator, which I am going to rewrite with clarity, e is for minus iota theta by 2 into 2 times Sx divided by h bar, has now been written in a form such that there is some angle here. It's not theta, it's theta by 2. Our rotation angle is theta, but the angle that appears here is theta by 2. And we have an operator such that the square of this operator is identity. Now this operator, which is equal to this operator, does a rotation through theta. But in the exponent there is a theta over 2 because we have to artificially put in a 2 next to this spin operator. So that I can make this matrix such that its square is identity. Now this operator is analogous to what I have written here. And I can use the theorem that I have proved to write this down as cosine of theta by 2 identity minus iota sine theta by 2. This is simply sigma x. So this is r x through theta. Remember this, a rotation through theta, but here the angles are theta by 2. ये बात समझ आई? इसको मैं 1 मिनट देता हूं आपको जज्ब करने के लिए, आप इसको देखेंगे. Let's take the block sphere initial state is kept z. Okay. Now I do a rotation r x through an angle theta on the state z. Okay. Now my rotation operator or the unitary operator corresponding to rotation is given by this. So I have my new state is cosine theta by 2 identity minus iota sine theta by 2 sigma x acting on head z. Now when this operator acts on z, nothing happens to z. Minus iota sine theta by 2, and what is the result of sigma x acting on z? Iota minus sigma x acting on z. I have to calculate this. Sigma x is simply z minus z plus minus z z. Okay. Now when sigma x acts on z, I get minus z. देखो sigma x की मैट्रिक्स फॉर्म ये है ना. When this acts on z, I get 0 1 minus z. I've done it in matrix form here and I've done it in Dirac form here. Okay. So sigma x acting on z gives you minus z. Sigma x is just like a NOT gate. Converts z to minus z. Converts minus z to plus z. So the answer for this is minus z. ठीक है. तो देखो जो रिजल्ट आ रहा है r x acting through an angle theta acting on z gives you cosine theta by 2 z minus iota sine theta by 2 minus z. If my theta is pi by 2, if my angle of rotation is 90 degrees, then my final state, psi final, is going to be what should I put here? Pi by 4, which is 1 over under root 2. Cosine of 45 degrees is 1 over under root 2. 1 over under root 2. 1, this is z. This is also 1 over under root 2, but this is minus iota. Minus iota minus z. But this is exactly this point on the block sphere. So my axis of rotation is along the x-axis. This is my initial state. This is my initial state. This is my axis of rotation. And I'm rotating through an angle theta. Yeah, I'm using. So this is my axis of rotation. Axis of rotation, fingers in the direction of the initial state, and I rotate like this, I end up here. So my state ends up here. And this point on the block sphere represents a quantum state which is exactly equal to psi final. And you will notice that this is equal to minus y. It's an ideal state of the sigma y operator. Okay? If I do a rotation through pi, this is pi, then this becomes non-existent. This becomes minus iota into sine of pi. Sine of pi is minus 1. So I end up with plus iota minus z. The global phase doesn't matter. Now this is something very interesting. ये बात यहाँ तक समझ आएगा? अब
Sine of pi by 2 ही है. Pi by 4.
If ये बात समझ आ रही है यहाँ पे? शाबाश. पसंद. ये बात समझ आ रही है? अब आप आगे चल रहे हैं ना कि जब pi होगा तो क्या होगा? When I'm making a rotation through an angle of pi, what's going to happen? If my theta equals pi, then my final state, psi f dash, right? I put pi in here. This becomes 0. This becomes minus iota. Sine of pi by 2 is 1. So I get minus iota into minus z. Now, how do we represent this point on the block sphere? It's just the south pole, even though there is a minus iota with it. Because this is just a global phase. This is really equal to e raised to power minus iota pi by 2 minus z. This minus iota equals this. But this is a global phase. Okay? So, this point, z, this point is minus z. But this point could be any ei alpha minus z. Because this global phase doesn't really matter when we talk about quantum states. समझ गई बात? अब मैं स्पिन हाफ का मतलब आपको बताने लगा। देखो चूंकि स्पिन हाफ पार्टिकल है ना, यहाँ 1/2 के फैक्टर्स आ रहे हैं। If I rotate through 2 pi, what is my final state? It's going to be, this becomes cosine of pi, which is minus 1. I get minus z. This becomes 0. Now where is this point represented on the block sphere? It's a north pole, albeit with a global phase factor, which is ei pi. So I make a rotation on this block sphere of a spin half system through 2 pi. I recover the original state, but a phase factor of pi appears, a global phase, which is immaterial for most purposes. But still there is a phase factor. If I make a rotation through 4 pi, only then my final state is going to be plus z. So this is what a spin half system means. You have to make 2 complete revolutions to recover your original state to the same global phase. Real objects, if I have this object and I rotate by 360 degrees by 2 pi, I recover the original state because this is a spin 1 object. If I have a spin 2 object, I rotate it through 180 degrees, I will recover the original object. If I have a spin half object, I will have to rotate it through 2 cycles to recover the original state with the same global phase. This is what is meant by a spin half object. Okay? Now we'll have a break. We'll meet at 20 minutes past 6. We'll break for namaz. And then I would like to talk about a quantum logic gate called the Hadamard gate. Okay, so let's meet at 20 past 6. Alright, so based upon the knowledge of the block sphere and the rotation operator, we can start talking about logic gates. And logic gates is something very familiar to you. In classical computing, you can talk about, for example, a NOT gate. Right? Associated with this NOT gate, there is a truth table. So there is an input 0, it gives you an output 1. Input 1 gives you an output 0. Since we're talking about binary logic, there are 2 input states. Now if this were to be replaced by a quantum NOT gate, then input cat 0 would give me cat 1, cat 1 would give me cat 0. Where zeros and ones are the labels of the orthogonal states that span that basis. Okay. So if we're talking about spin half systems, for example, what a quantum logic gate, a NOT gate would do is that it would take, so let's denote that gate by U, and I call it N, just to specify it's a quantum NOT gate. So what this gate would do, it would act on plus Z, and what would the result be? Vishal, aap batao. देखो अगर 0 को 1 में बदल रहा है, orthogonal state में बदल रहा है, तो the NOT gate, the quantum NOT gate is acting on get Z. What should be the output? The orthogonal state. जो state इसकी orthogonal है, वो कौन सी है? माइनस Z, ठीक है? और the NOT gate should act on minus Z to give you plus Z. So if I would like to represent this NOT gate in a basis, which is the Zeeman basis, right? What would the matrix look like? 0, 1, 1, 0. This is the output when this is the input, and this second column is the output when this is the input, right? Or you could do it by a calculated method. This element is simply UN acting on Z, projected on Z, right? This element is UN acting on minus Z, projected on Z, and so on, okay? So you can use this formalism to calculate what the NOT gate looks like. So the quantum NOT gate has this operation. You need to define these operations on the two orthogonal states to completely define the quantum NOT gate, or any gate.
So why are Z and X and Y not orthogonal?
Because, that's a very good point, because cat H and cat B are orthogonal, right?
Yes.
The analog to cat H is plus Z, the analog to cat B is minus Z. Right? These states are orthogonal. Why are they orthogonal? Because SZ, the operator SZ has two eigenstates. One of them is plus Z, right? And the other is minus Z. Okay. Now, the eigenvalues associated with SZ are plus h bar 2 and minus h bar 2. They are distinct. Hence, the associated eigenstates must be orthogonal. We label one of these states as plus Z and the other state as minus Z. These are just labels. Because our conception of three-dimensional Euclidean space dithers away, it fades away. No longer talking about the geometrical Euclidean space. Plus Z and minus Z are just labels to the eigenstates of the SZ operator. Okay? And plus Z in physical sense would correspond to a spin whose magnetic moment is parallel to the magnetic field gradient, and minus Z is a spin whose magnetic moment is anti-parallel to the field gradient. And when you pass them through a spin analyzer, through a Stern-Gerlach experiment, we've done those experiments. You will notice that if you block one beam, you have the other beam, you have the plus Z beam, there is no possibility of getting minus Z on subsequent spin analyzer. Hence, plus Z and minus Z must be orthogonal. Okay. So this is the physical motivation. Okay. ये ना सोचो कि X is orthogonal to Z. These are just labels. X is orthogonal to minus X. These are just labels, by the way. But there is a physical underpinning as well, which I've just highlighted again. ठीक है? अब ये हमारे पास quantum NOT gate है, जिसका मैट्रिक्स फॉर्म ये है in a particular basis. और ये operations on the orthogonal basis states completely define what is meant by a quantum NOT gate. Now we would like to know how do we implement such a gate. इस गेट को हम implement कैसे करेंगे? ठीक है? तो all implementations of a single qubit are unitary operators. They are rotations of the Bloch sphere. So if you look at this prescription, what we would like is to define a Bloch sphere, and what should the quantum NOT gate do? if the initial state is plus z, if a NOT gate acts on it, what is the final state? Minus z. You should end up here. So what a NOT gate should do is, it brings this state up to here. Right? So the action of a NOT gate should be to start off with z and bring the state down to the south pole, to its orthogonal state. And if you have this initial state, it should bring it back up to the plus z state, right? This is what the quantum NOT gate should do. Now can you think of a rotation operation that does this? It's a rotation about pi.
एक्सेस तो कोई भी चूज कर
अच्छा y चूज कर लें, चूज करके देखते हैं, ठीक है? Let's choose this axis, y, the y axis, and let's propose that our y act through an angle of pi by 2. Let's check whether this qualifies as a NOT gate. Okay, let's check this. ठीक है, ये proposed है कि this rotation through 180 degrees about the y-axis, let's see whether it qualifies as a NOT gate or not. ठीक है? So when this operation acts on plus z, ry through pi acting on plus z, you get minus z. ठीक है? Rotation through 180 degrees, you add plus z, you go to minus z. अब अपनी कैलकुलेशन करने की जरूरत नहीं है, करना चाहें तो कर लें, लेकिन जरूरत नहीं है कि it's just a rotation through 180 degrees about the y-axis. So your head must end up here. If you are at minus z, ठीक है, where would you end up? You end up here. Okay, you're down at the south pole, you're doing a rotation about this axis, right hand rule, end up back at New York. End up back here. So it seems, it appears that this rotation through the y-axis, through an angle pi, qualifies as a legitimate NOT gate. But let's see what this rotation does to an arbitrary state, because the NOT gate should be universal. Any input state, it should give you its NOT, its inverse. So if you have, if you have your theoretical NOT gate, and if it acts on z plus minus z under root 2, which is simply state x, what should the output be theoretically? ये रहनी चाहिए, क्योंकि un acting on z gives you minus z, un acting on minus z gives you plus z. So your output theoretically should be z plus minus z over under root 2. In other words, this state must be an eigenstate of the quantum NOT gate. It should leave the state unchanged. Now let's see if our rotation operator, our candidate rotation operator through pi, what does it do to a z plus minus z state? We can perform this calculation, or we can look at the plot sphere. Our initial state is here. Now you're doing the rotation through pi about the y-axis. You're here. So where do you go? You end up at minus x. Okay, but what is minus x? Minus x is simply z minus z under 2, which is not the same as what you would expect because the relative phases are totally different. Hence, this gate, this rotation through the y-axis does not qualify as a legitimate quantum NOT gate. Okay. Another way to look at this is the following. Let's look at r by pi and let's use our theorem, our celebrated theorem. This is equal to E minus I pi s y over h bar. Right? This equals cosine of pi over 2, right? Half of this angle, identity, minus iota sine of pi over 2 and sigma y. Okay, this is the rotation operator. This rotation operator is equal to this. Let's see what the matrix form of this operator is. This is 0 minus iota sigma y. Let's see what this factor is. It's minus iota. Let's put this in its representation 0 minus iota, iota 0. This gives me minus iota multiplied by minus iota is minus 1 हो गया 0 minus 1 और ये क्या हो गया 1 plus 1. Is this matrix the same as the matrix that we intend to achieve? It's not. It's not. There is a minus sign here. There is a misbalance of minus sign, of a phase here between this element and this element. If we were to construct a true quantum NOT gate, there should be no phase imbalance between these factors. And these diagonal elements should be 0. So this 180-degree rotation on the y-axis does not constitute a quantum NOT gate. So we have to be careful about the axis of rotation if we would like to implement certain gates. Okay? Now let's choose another candidate. Let's say, if I have a rotation about the x-axis and I give a rotation to pi. Okay? Still, z goes to minus z under this. Minus z goes to plus z under this. Okay? So we're okay, but the 180-degree rotation about the y-axis was also okay up to this point. So let's see what this rotation would do to plus z plus minus z over under root 2. It will recover the same state. Because now what you're doing, this state, if you look at the block sphere, pi is here, this is x, and the axis of rotation is also along x. So this state remains unchanged. Hence, this state remains unchanged as it should. So the 180-degree rotation about the pi axis does qualify as a legitimate quantum NOT gate. We can also write down the matrix Rx pi equals cosine pi by 2 iota, which is 0, minus iota sigma x. सैंडविच वो थ्योरम इस्तेमाल करो, ठीक है, माइनस आयोटा इंटू साइन पाई बाई 2 इंटू सिग्मा एक्स. ठीक है, अब माइनस आयोटा सिग्मा एक्स क्या है 0 1 1 0. Now is this the same as the gate that we intend to achieve? Yes, it's the same. This factor of minus iota is global. It doesn't affect the state. Right? And there is no misbalance in phases between the elements of the matrix. So this does achieve a quantum NOT gate. समझ आई बात? So a 180 degree rotation about the x-axis is a quantum NOT gate. A 180 degree rotation about the y-axis is a quantum gate. You have to be careful about the phases. This is not a geometrical Euclidean space in which the x-axis and the y-axis are the same. There are phase factors that differentiate between the different axes. So now we've constructed a quantum NOT gate through a rotation about the x-axis through pi, through an angle pi. So suppose you're here. Okay, you're here. This is a certain point, and you do a 180 degree rotation about the x-axis. Okay, so you will end up here. You go from here, here, and you'll end up here. Because this is your axis of rotation, so somewhere here, go like this. Okay? This is your axis of rotation, you rotate through 180 degrees, you will end up here. So this state will be transformed to this state, and this state, okay, where will you end up? You will end up towards the back, you will end up towards the back. And this final state and the initial state will be 180 degrees with respect to one another. They will be orthogonal.
So your y-axis get around.
So वो NOT gate नहीं बनेगा. If you're here, suppose you're here. Suppose you're, let's keep it simple. Suppose this is your state. Your initial state is y. And this is your axis of rotation. Where will you end up? You will go all the way here and you will end up at minus y. This is simpler to understand, okay? If you had a 180 degree rotation on the y-axis, this state will remain unchanged. But that's not allowed because this state is simply ket z plus iota minus z. What you intend to achieve is that this plus z should go to minus z and this iota should remain unchanged and this minus z should go to plus z. And what is this equal to? This is iota, I take common, z, यहाँ पे क्या करूँ? Minus iota, minus z, which is different from the state that you intend to achieve. So 180 degree rotation on the y-axis is not a quantum NOT gate. But a 180 degree rotation about the x-axis is a quantum NOT gate. Now, a very important gate that is used in quantum computing and will also set the stage for the study of entanglement, which is a purely quantum mechanical phenomenon. The weirdest of all phenomena is the understanding of a Hadamard gate. Hadamard mathematician का बहुत मानो. अच्छा, Hadamard gate क्या करता है? It prepares superpositions. It's just like a beam splitter. So if you input say plus z and you have a Hadamard gate UH, what this will do is it will prepare a superposition ket z plus minus z under 2. Okay? यानी अगर इसमें horizontally polarized light इस Hadamard gate में दें, you will get horizontal plus vertical 45 degrees polarized light over under 2. Okay? Or plus z spin state, then you will get x spin state at the output. Likewise, if this gate acts on the minus z state, you get z minus under root minus z under root, right? So this is how we define the Hadamard gate. Somebody? तो इसका अगर आप मैट्रिक्स फॉर्म लिखें in the Zeeman basis, what do you get? 1, 1, 1, minus 1. Now this is our definition for a Hadamard gate. यानी अगर मैं बीम स्प्लिटर की बात करूं, just to motivate you physically what's going on. If I have a beam splitter and I take this path, I label it alpha and I label this path as beta. If my input is ket alpha, my output is going to be, now I label this path as alpha dash, this path as beta dash. If my input is alpha, my output is alpha dash plus beta dash. And I don't need to use these apostrophes, in fact, these are just labels. And if my input is beta, my output is going to be alpha dash minus beta dash over under root 2. We've done homeworks and quizzes of this kind, right? So this beam splitter is a Hadamard gate. And now we're talking about the path of the photon, the degree of freedom, the relevant degree of freedom to the path of the photon. So a Hadamard gate is defined by this truth table. This is just like a truth table. What does it do to the orthogonal states that span the basis? Okay. So what will the Hadamard gate do to a superposition? If you make the Hadamard gate act on this state, what should you get? You should get back Z, right? Alpha plus beta पे act करें दोबारा alpha मिल जाएगा, ठीक है? If you act the Hadamard gate on this state, you will get the minus Z. मैं आपको 2 मिनट देता हूँ, बहुत जरूरी है इसको समझना, मैं बहुत तेजी से चल रहा हूँ, तो इसको समझ लो. मैंने यहाँ पे सिंपली ऐड किया है इन दोनों को ऐड करेंगे, ये कैंसिल हो जाएंगे, कैट Z रह जाएगा.
So in horizontal vertical terms, if you were to input a horizontal state, you get 45 degrees.
So in horizontal vertical, if you're more comfortable with this, a Hadamard gate acting on ket H gives you H plus B under root 2, right? A Hadamard gate acting on the orthogonal state B gives you ket H minus ket B under root 2. Okay? What will happen if UH acts on ket H plus ket B under root 2? You get back ket H. ठीक है, इसको इस पे एक्ट करो, लेता इस पे एक्ट करो, लीनियरिटी का प्रिंसिपल अप्लाई करो, you get back ket H. ठीक है, इसका मतलब ये है कि if I have an input state, say ket H, ठीक है, I have a Hadamard gate UH, right? Now this is what I'm drawing is called a quantum circuit. I input this quantum state into this gate, I get a new state, which is this, right? 45 degrees polarized state. ठीक है, समझ आ गई? अब एक मैं इसी स्टेट में दोबारा एक Hadamard gate अप्लाई करता हूं, तो क्या मिलेगा मुझे? I get back this state, get H. So the Hadamard operation is such an operation which is self-inverse. UH, inverse of UH is UH itself. Okay? It's a self-inverse. And this is actually UH dagger as well. देखो, दो gates back to back लग रहे हैं. The second gate is inverting the effect of the first gate. So it's a self-inverse. इस मैट्रिक्स का inverse निकालो. लीनियर अलजेब्रा की कवायद को सामने रखते हुए तो वही मैट्रिक्स आता है. इसका ये वाला कॉलम और ये वाला कॉलम ऑर्थोगोनल है. इसकी ये वाली रो और ये वाली रो ऑर्थोगोनल है. ऐसे मैट्रिसेस को लीनियर अलजेब्रा में Hadamard मैट्रिसेस कहते हैं. ठीक है, ये हायर डायमेंशन. But this is the Hadamard gate. Now by looking at this truth table and looking at the diagram of a block sphere, I would like to choose a rotation that does the trick of a Hadamard gate. What kind of rotation do I need? Just think about it. I want to do a rotation that does a Hadamard gate on an arbitrary input state, and I achieve the effect of the Hadamard gate. R by 90. अच्छा, ये लॉजिकल पहला यही एक अच्छी बात आपने ये, क्योंकि ये एक नेचुरल इंट्यूटिव आंसर है कि ये y एक्सिस है. If I do an R by 90 degrees, okay, I start with this state, I reach here. But the problem is that if I have this input, I will go to this state. But what I would like to do, I would like to go back to the input state. Is there an operation about a certain axis through a certain angle that achieves the effect of Hadamard gate? Rotation of वो unitary नहीं होगा. You need a unitary gate. All gates are unitary. They have to be unitary because quantum mechanics is reversible. ये हम पढ़ेंगे.
और एक सौ और वही को ऐड कर.
ऐड करने में क्या मतलब?
ऑपरेटर्स को ऐड.
अब शाबाश, एक ऑपरेटर ऐड नहीं कहते. एक ऑपरेटर के बाद दूसरा ऑपरेटर है. Let's have a tandem of operators. Let's do multiple rotations. Okay? So I propose something. If I have this input, I would like to go here. If I have this input, I would like to go back here. If I have this input, beta, I would like to go to the back. And if I have this input, I would like to come here. So what I would propose, let's do a rotation R about the y-axis through 45 degrees. Okay? So if I'm here, I end up here. Okay? I don't quite reach the equatorial plane, but I end up such that my angle, this angle is 45 degrees. Okay? So I start here, instead of going all the way to the equatorial plane, I end up at 45 degrees. Now let's do another operation. Let's do a 180 degree rotation about the x-axis. ठीक है? तो इस operation के बाद I would like to do a 180 degree rotation about the x-axis. Since I apply this rotation first, it comes to the right, then I apply this rotation. So it comes to the left. This is how operators are ordered. The quantum state is somewhere here to the right. So first you apply this, then you apply this. So if I apply this rotation, now this is my axis of rotation and I end up in the southern hemisphere. Here, right?
So shouldn't go back?
No. Because my axis of rotation is now the x-axis. देखो, मैं ये x-axis है बिल्कुल ठीक है, और ये z-axis है. मैं यहाँ से चला 45 डिग्री तक. अब ये मेरा axis of rotation है. अब इसके गिर्द मैंने कोण में 180 डिग्री मूव करना है. अब एक कोण बनाता हूँ जिसका वर्टेक्स ये है.
सर बट RX पाई जो है ऑर्थोगोनल स्टेट नहीं देता था.
RX पाई जरूरी नहीं है कि ऑर्थोगोनल स्टेट है. वो सिर्फ जो आइगन स्टेट है ऑर्थोगोनल स्टेट है. ठीक है, आप चेक कर सकते हैं इसको. तो अब यहाँ पे मैं रुका. I do a rotation with 180 degree about this axis. Now this is my axis. अब एक कौन समझो जिसका वर्टेक्स मेरा O है, ठीक है, और ये वो एक्सिस है, ये मेरा पॉइंट है. I rotate by 180 degree, I come back here. Now I would like to come back here. So I need to do another rotation. What kind of rotation do I need to do? And now I'm here, I would like to come here. What should I do next? Right, to minus 45 degrees about the y-axis. So that I can come back here. Okay. So then I have R about the y-axis minus 45. Okay. So this action, when it acts on plus z, I would get this state, which is in shorthand x. So this sequence of operations is performing a Hadamard gate. Now let's check this out. If I start off with this state, where should I end up in a theoretically correct Hadamard gate? I should end up here. Let's see if this sequence of operations, these cascaded rotations, affect the Hadamard gate or not. So I'm here. First I do a 45 degree rotation. I would like to do another block. I'm here, okay? This is my y-axis. I do a 45 degree rotation, the same operator, the same sequence of operations, because the same sequence of operation must apply to any input state. I don't want to change my sequence of operations with different states. My sequence of operations must be universal. So I do a 45 degree rotation about the y-axis. Now this is my y-axis, I'm here. Wait, I end up in the southern hemisphere. Through 45 degrees. I end up here, right? This is the first operation. Number one. Now I would like to do a 180 degree rotation about the x-axis. Now this is my axis of rotation. This one. I'm here. I'm down here. Where would I end up? This is my axis of rotation. I will go all the way back up to the north hemisphere. I will end up here. Second operation. ठीक है, मैं यहाँ था, ये मेरा एक्सिस रोटेशन है. I end up in the northern hemisphere at an angle of 45 degrees. Now I would like to go back here. So I again do a 45 degree rotation, minus 45 degree rotation about the y-axis. I come back here. This is the third operation. So right, I can make a cone, right? This becomes a cone, right? I can do a 180 degree rotation about this tilted axis and I can achieve a Hadamard gate. I'll try to come up with an animation that shows this. So this 180 degree rotation of the tilted axis qualifies as a Hadamard gate. मैं इसको बना भी सकता हूँ ऐसी बात नहीं. ये मेरा एक्सिस ऑफ रोटेशन है, ठीक है, और 180 डिग्री की रोटेशन अबाउट दिस एक्सिस कर रहा हूं. आई कैन कंस्ट्रक्ट अ कोन, a tilted cone which has its opening at 45 degrees. So I start here, I do a 180 degree rotation, I end up here. And if I'm here, I do a 180 degree rotation, I end up here. So this becomes my axis of rotation. So there is a single axis of rotation and a single rotation that also qualifies for a Hadamard gate. And if you would like to try to operate it for this, e raised to power I minus I, what's the angle of rotation? Phi. Now I have to choose an axis of rotation. It's not Sx, it's not Sz. It's in between Sx and Sc. It's actually, so I write the h bar outside, it's actually Sx cosine of 45 degrees, which is 1 over under root 2, plus Sz 1 over under root 2. This operation does the trick for a Hadamard gate. The axis of rotation is defined by a combination of Sx and Sg. Okay? And you can check that if you take the square of this divided by h bar, you multiply by 2 as well, it will be identical. Okay, so this is the Hadamard gate. Aakhri point, we should always finish on something really interesting, so that we have a reason to come to the next class. Suppose I have not one spin half, but two spin halves, or two qubits. Okay? You can have two spins, two electrons close together, talking to one another. These are two qubits. Okay? This is a Hadamard gate, UH, just on one qubit. Now I label the states for generality as alpha and beta, right? These are my basis states. Okay? Instead of z and minus z, I call alpha beta. Suppose this is qubit or spin half or fictitious spin half in state alpha. This is also in alpha. Okay? So the quantum state here, the first qubit is in alpha. The second qubit or the second spin half is also in alpha. So I write ket alpha followed by ket alpha. This represents, this is the first qubit, this is the second qubit. Okay, this is just notation. I will have more to say about this notation. Okay, or I can write this in condensed form as alpha alpha. Okay? The first position is for the first qubit, the top one. This is for the second qubit. Now I do a Hadamard gate only on the first qubit. Okay? I would like to find out the state here. I am not measuring any qubit. So the state is nothing, it's not collapsing. So here the state, what is the state going to be? Nothing is going to happen to the second qubit. There is something that is going to happen to the first qubit. The Hadamard gate will create a superposition. It will create alpha plus beta, right? Over under root 2. This is the first qubit, and the second qubit I write just like I would normally do. Okay? Now I can write this in condensed form as alpha alpha plus beta alpha over under root 2. Okay? Now I do another gate. What I do next is that these qubits go on, I apply a gate which is called a controlled NOT gate. What the controlled NOT gate does is, if the first qubit is in the state alpha, it does nothing to the second qubit. If the first qubit is in the state beta, it creates the orthogonal state that is orthogonal to this qubit. Or it applies a NOT gate to this qubit. Okay? So if my input, if I have a C0 gate, okay, my input is 0, 0. Nothing happens to the first qubit. Never happens to the first qubit, but nothing happens to the second qubit. Or okay, alpha alpha. If this is alpha alpha, my output is also alpha alpha. If my input is alpha beta, my output is alpha beta, right? Because the first qubit is the control qubit. It's in the state alpha, nothing happens to the second qubit. However, if my input is beta alpha, now the control qubit is in beta, so it's going to apply a NOT gate to this qubit, to the second qubit. It will create beta beta. Okay? If my input is beta beta, the control qubit is beta, so it will apply a NOT gate to the second qubit. It will create beta alpha. Now if I apply this NOT gate here, I would like to find out the final output state. So this is the input here. Nothing happens to this part. It remains alpha alpha because the first qubit is in the state alpha. But here the second qubit, the first qubit is in the state beta, so it must apply the NOT gate to the second qubit. So I will get beta beta. Now look at this. The classical NOT gate is acting on the superposition. Alright, now this is your final state. If these are two qubits, two spin half particles, I keep one particle with me on Earth and send the other particle to the moon. And if I place a detector here that measures in the alpha beta basis, how many possible outcomes do I have for the second qubit? I'm measuring in the alpha beta basis, which means I'm applying an experiment that can break this qubit into the alpha channel and a beta channel. What are the possible outcomes? Alpha or beta. And what's the probability? 50%. I can either get alpha here or I can get beta here. But the point is that if I measure alpha, if this detector clicks, then no matter wherever this second qubit is, you don't have to detect it. It will automatically be in the alpha state. Because of this, because you're collapsing into this wave function. The collapse is such that you measured the second qubit to be in alpha, so this state is collapsing into this state upon the measurement. You're preparing a new state. So the first qubit in this new state has to be in the state alpha. You measure it or not. If you measure it, it turns out to be in the alpha state. Because this detector has clicked. If by chance there is a 50% probability that this detector clicks, and if this detector clicks, you're collapsing the wave function into this state. The first qubit, no matter where it is, beyond the confines of distance, ज़मानो मकानी हदों से आगे जहाँ भी है ये qubit, अगर ये detector click करेगा, तो this qubit will appear in the state beta. If you measure it, it will be in the state beta. Now there's a 50% probability. It's a totally random probabilistic event. But whatever outcome you get, there's some correlation with the other qubit that's far away. Sometimes you get alpha, but if you get alpha here, a measurement here will yield get alpha, always. You measure get beta here, the measurement will yield get beta, always. But this qubit is physically distinct from this qubit, far away. It doesn't know what you would measure here. But there is some spooky correlation, quantum correlation between these two qubits, which cannot be explained classically. And this is the phenomenon of quantum entanglement. The weirdest phenomenon of quantum mechanics. Okay, and we'll have more to say about this in this course. So inshallah, see you after the midterm break.